Okay, this is chapter 10, Forces and Motion. We're looking at the sixth and final section. It's about pulleys. There are two scenarios with pulleys, really. The first one is this kind of scenario. We have a smooth pulley. So this thing here is smooth. It rotates freely. There's no friction around here. On either side of the pulley, you have two inextensible strings, which are light, they don't weigh anything, and at the bottom of each string you have a weight. So that's our scenario. The example I'm going to do to help us understand this is example 13 on page 173 if you've got the Pearson textbook, example 13, page 173, but I'll talk you through it if you haven't anyway. So we've got particles P and Q of masses 2m and 3m. So in this particular example, you're not given the exact masses. You were just told that this one is 2m and that one's 3m. So we have forces pulling down on this one of 2mg due to gravity, and this one is 3mg due to gravity. So that's the start of our forces diagram. The forces diagram on a pulley can get a little bit complicated. So these are attached to the ends of a light inextensible string. The string passes over a small, smooth, fixed pulley, and the masses hang with the string taut. The system is released from rest. So there'll be something about initial velocity being naught somewhere along the line. Okay, our first thing is to write down an equation for the motion of P and write down an equation for the motion of Q. Well, let's sort our diagram out first. Let's think about this one. Because this is lighter than this weight is lighter than this one, let's assume that once we let go that it's going to move this way. It's going to accelerate this way. So this one is going to be accelerating upwards. So we need a little acceleration diagram, double-headed arrow. That's going to be A. Likewise, we need a little double-headed arrow coming down this way, because the motion's going to be going that way. Whoops, that way. What we also need here is some arrows for the tension in the string. Now, if we consider this weight, the rope is pulling it upwards like that. And presumably this one also, the string is pulling it upwards because it's slowing it down. Obviously, if we didn't have a string, this would fall at 9.8 meters per second. It's not going to fall as quickly as that because there's an upward tension. We've got a downward force here and an upward force, which is the tension in the string. Sometimes we need to consider what's happening on the pulley. You know, what is the force on the pulley? And the force on the pulley is caused by the tension downwards here. So pulling on that side and pulling down on that side. And all these tensions are the same. The only case where these are not the same is if either of these two weights lands on the floor, in which case the tension in this one disappears momentarily, and tension in this one disappears until this one falls back down and they're tight again. Or if the string is extensible, if it's springy, or if there is some friction in our pulley. In this particular chapter, the pulleys have no friction, they are smooth, and the strings are inextensible. So we can consider information about the pulley separate to these two if we wish. We can consider three separate areas if we want to, but the tension, we must remember, is going to be the same for all these. Okay, we need to write down an equation for the motion of P. Let's have a look at the motion of P. Well, let's do the resultant force, and because the motion is upwards, the acceleration is upwards, we're going to consider upwards as positive. So this tension here is positive, this is negative, minus 2mg, so the force upwards, the force downwards, T take 2mg equals the mass times acceleration, 2m times the acceleration, which is A. That's for P. Let's consider Q. Now, because the motion is going this way, I'm going to consider downwards as positive. So, resultant force downwards for Q. Well, it's going to be, this is now positive, so 3mg is the force downwards. Take away the tension going upwards is mass times acceleration, 3m times a. So that's how we can write our equations of motion, and we can now use these to find out what A is. Now, if these two tensions are the same, then we can just solve these simultaneously, add them together, or whatever we want to do. Let's add these two together. So we're going to have 3mg take 2mg, I'll take that one, take that, take 2mg, 3ma, we've got to be careful here because, sorry, I'm not taking them together, I'm adding these together, I do apologise, I'm adding these two equations together to get rid of the t's. So 3mg, add minus 2mg, add the minus t to the t, they cancel, 3ma plus the 2ma. So I have got that mg equals 5ma. They cancel, let's cancel, and acceleration is g divided by 5. I can just write it as g over 5, I don't need to actually work out what it is quite yet. So the acceleration of P and the acceleration of the Q, because of the same, is the fifth of acceleration due to gravity. So 9.8 divided by 5 if you wanted to work it out. Right, now we're going to find the tension in the string. Well, now we know what A is, we can put it back into one of these. So let's just put it back into the first one, shall we? See what happens. So T minus 2mg is 2m times A, which is g over 5. Right, we just need to play around with this a little bit. So the tension is 2mg over 5 plus 2mg. Well, that's 10 fifths. 11, 12 fifths, so T is 12 fifths of mg, and you could work out 12 fifths of 9.8 if you want, or you can leave it as that. So that tells you what the tension in the rope is. Now we can also use this information to work out what the force exerted on the pulley by the string is. Well, it's quite easy to see. If you've got T pulling down here, which is 12 fifths of mg, and T pulling down here, which is also 12 fifths of mg, then the force on the pulley is 2 lots of 12 fifths of mg, which is 24 over 5 mg. Again, you could do 24 fifths of 9.8 times m and work it out that way. Let's do some more calculations here. In this particular example, part E says find the distance moved by Q in the first 4 seconds, assuming that P does not reach the pulley, and also assuming that this does not hit the ground, if in fact there is a ground. So let's assume in the first 4 seconds there's still free movement. Okay. So let's see what we have got. It started from rest. This is part E. It started from rest. So U is 0. Acceleration we know is a fifth of g, or g over 5. What else do we know? We're looking after the distance after the first 4 seconds. So we want to find S. So let's write down all that stuff. V, the final velocity we're not asked to find, but we don't have it, so it's probably going to be of no use. I want an equation that links these things together. Well, this one jumps out of it. S equals ut plus a half a t squared, which is 0 times 4 plus a half times by g over 5 times by t squared. So let's just work that out. 0 times 4 is 0, obviously. This is g over 10 t squared. So t equals the square root of what am I doing here? T is 4, so I should have a 4 there. Come on, sort yourself out. So the distance is 16g over 10, 1.6g, so s is 1.6g. Whoops. I hope your working's neater than mine. 1.6g. So 1.6 times 9.6 is approximately 15.7 meters. You will be almost always be asked, state some assumptions about your model, or however use the fact that the pulley is smooth or something. Well, if the pulley is smooth, then the tensions are the same. There's facts like that which you might need to pull in, or the fact that the string is light means you don't consider its weight into your calculations, but there'll be some kind of model analysis you'll have to do, which might concentrate on a limitation of your model. So a limitation is that we haven't considered friction, that the string is inextensible. It's very tricky to get a string which is completely inextensible. But these are limitations of our model. But for a starting point, let's get to grips with these basics.